Hello. This week's topic is energy. But don't forget we'll talk about only mechanical energy since we are studying mechanics course. Energy, mechanical energy. So as you know, there are so many types of energies: chemical energy, nuclear energy, light energy, sound energy, heat, etc. But today we will talk about only mechanical energy. There are some kinds of mechanical energies. The first one, famous one, is kinetic energy. Kinetic energy. Kinetic energy is the energy of the motion, mass times velocity square or speed square over 2. So this is the kinetic energy. If something or someone moves with certain velocity, and if this object or person has mass m, then it means this object is carrying kinetic energy, mass times speed square over 2. Second type of the mechanical energy is the potential energy. Potential energy, mass times gravity times height. Basically, this is the energy due to the position. So, for example, we have a table, surface, and we have an object at this point. Yes, if you leave this object, if you release, it will fall downward. Why? It means initially at that point it had some energy, otherwise it won't fall. So it means this energy, basically we call it potential energy. It depends on mass, on gravity, and height. And there is also potential energy of the spring. Potential of the spring, kx square over 2. Spring, you know, this is a spring. This is, let's say, unstretched. It was not extended, it was not compressed. So this is its original length. When you apply force to the right, for example, what will happen? It will extend. Yes, length will become longer. So this is extension. Let's call it x. And the spring has a constant, yes, k. So k times x square over 2. Here x is a, don't confuse, this is not length of the spring, this is the extension. How much it was extended or how much it was compressed. This is also mechanical energy. And there is a work. What is a work? For example, in order to move this object for a certain distance, you need to apply forces and it will move for a certain distance x. The person that applies this force needs to spend some energy. Yes, or we can say this force do some energy, and this energy has a special name, we call it work. So this work, basically this is energy, also type of the energy, force times distance. So as you see, we have some main mechanical energies: kinetic, due to the motion; potential energy, due to the position, height, and the potential energy of the spring. When you compress or extend the spring, it will receive some kinetic potential energy. And the last one, work. When you apply force and this object moves, then it means this force is doing some work. The main point in energy is conservation of energy. Conservation of energy. What is a conservation of energy? What is the idea of conservation of energy? As you know, energy cannot be created from nothing, or energy cannot disappear. Yes, only what happens, energy transforms from one type to another type. For example, kinetic energy can transform, or it can become potential energy, let's say. Yes, or let's write in this way: in kinetic energy, it can become potential energy. Potential energy, it can be converted to the spring potential energy. Spring potential energy can be converted to the work, etc. So order is not important. Potential energy can be converted or transferred to the kinetic energy, etc. Basically, let's say initially system has a 100 joule. Yes, this energy of the system will be always 100 joule, always. The point is 50% it can be kinetic energy, yes. 30 joule it can be potential energy. Other 20% it can be work, for example. It may belong to the work. So the sum of the all energies should remain constant. It should not change. It cannot be increased. It cannot be decreased. The summation of all types of energies should be always constant, and we call it conservation of the energy. For example, free fall example. We have an object. It was released with from the height 20 meters. Find velocity, final velocity, or velocity just before striking the, just before reaching the table surface. You can solve it by using free fall equations. Yes, this is a motion with constant acceleration, and this acceleration is equal to gravity in this case. And also, alternatively, you can solve this problem by using energy method. Energy conservation of energy says that initial energy should be equal to final. So what is energy, initial energy? So let's say this is initial point, and this is just before striking the ground. Let's take it as a final. Finally, it will have some velocity. We should find this velocity. So what is initial energy? Initially it was at a certain height, so it means there was a potential energy. No kinetic energy because no velocity at the beginning. Now, when at final point height becomes 0, no potential energy, but it has a kinetic energy. So we need to write kinetic energy, mv square over 2. So mass cancels, so velocity square equal to 2 times gravity times height, and from here 2 times gravity height, answer will be 20 meters per second. So velocity of this object just before striking the ground equal to 20 meters per second. So as you see, you can solve this problem with just only one equation if we apply energy method. Another example. So you should not forget about this equation. This will always work. Initial total energy always should be equal to final energy. Let's give another example. We have a spring, initially unstretched, and we have an object moving with velocity 10 meters per second. Mass of this object is 10 kilogram. Spring constant of the spring is 1000. Question. What is the maximum compression of the spring? Maximum compression. What does mean maximum compression? When object will stop. Yes, when object stops, how many centimeters or meters it will compress the spring and it will stop. So this is initial case. Let's draw the final case. So spring will be compressed just like this. So for how much centimeters we don't know. For now let's call it just x. So this is x. We should find it, x. So according to the conservation of energy, we know that initial energy of the system should be equal to final energy of the system. So initially spring is unstretched. Yes, it means no potential energy of the spring. Object is moving, so we have only object's kinetic energy. Finally, at this point, object stops, no kinetic energy, but spring compressed, so it means spring has a potential energy. So from here, x square equal to mass v square over k. So x equal to v root square root m over k. So velocity was equal to 10, mass 10, spring constant 1000. So 10, 1 over 100. So answer 10 over 10. Answer is 1 meter. So spring will be compressed for 1 meter. Yes, after 1 meter it will stop basically. Now let me add one more question. what is the velocity of this object at the halfway? Or we can say find velocity of this object when spring compressed for 0.5 meter. So of course you can pause this video and you can solve, and later you can replay the video and check your answers, solutions. So again we will apply conservation of energy method. Initially object was moving, and initially we have only kinetic energy, and we know that at halfway, at 0.5 meter, object will be still moving. Yes, because it will stop after 1 meter. It means object has a certain velocity. It means kinetic energy. And also spring is already compressed for 0.5 meters, so it has a potential energy. Let's call it x1. Now we need to just solve these equations. Yes, we know that initial velocity mass equal to 10, initial velocity is 10 square, mass 10, velocity unknown for now, k is 1000, x is 0.5 square. So 1000 equal to 10 v1 square plus 0.25 250, so 750 equal to 10 times v1 square, so v1 square equal to 75, or we can say v1 equal to square root 75. It means 5 root 5. Yes, approximately we can find the approximate number, 8.6. So at midway, speed of the object will be 8.6 meter per second. It means, so in this way you can apply conservation of energy method. So as you see, we have just one equation, this one, and with the help of the one equation you can solve the problems. That's why energy method is very simple and it's very convenient. You don't need to worry about what kind of force applied by spring to the object, etc. Just we need initial point. We need to find all energies at the initial point, and we need to find all energies at the final point. That's all. They should be equal to each other. Very simple. Now let's solve some examples related to the work. Yes. So frictionless surface, and we have object F 100 Newton. Someone is applying 100 Newton. Of course, this object will move and find velocity of this object after 10 meter. So of course you can solve this one by using Newton's law, by using kinematics. First you can find mass. Mass also should be given. Yes, mass also should be given. Mass equal to, let's say, 20 kilogram. You can find acceleration, and you can apply kinematics equation. So at least you need to apply two equations. Now let's solve this problem by using just one equation due to the conservation of energy. So this is initial point. This is a final point. For example, it will be here and it will be moving to the right with certain velocity, and we should find this velocity after 10 meters. So conservation of energy states that initial energy should be equal to final. Initially it was stationary, no kinetic energy. What else? It's zero basically, yes, but someone is adding, someone is giving energy. Who is giving this energy? Of course, this force. This energy is coming from this force. This force is doing some work. So work for this problem will be initial, because someone is adding. So work will be here at the left side. You can assume it's initial, and this should be equal to final energy. Force times distance, this is a work, equal to finally it will be moving with a certain velocity. It means there will be kinetic energy. Force is 100, distance 10 meter, mass 20 over 2 times v square. So here we have a 10 cancelled, velocity square equal to 100. So from here velocity will be 10 meters per second, as you see, 10 meters per second. Now let's solve it by using dynamics and kinematics. Yes. So according to the Newton's second law, F equal to ma, 100 equal to 20 times a, it will accelerate with 5 meters per second square. Yes. Now we can apply kinematics second equation. V final square, V initial square plus, because velocity increases, 2 times acceleration times distances. Final velocity unknown, initial velocity is 0, 2 times 5 times 10. So as you see, V2 square equal to 100. From here, V also equal to 10 meters per second. So you can get the same answer. But by energy, it's very simple, just one equation. Another example, object moving with velocity v, let's say 5 meters per second, and here we have a rough surface. Rough means friction. There is a friction here. There is a friction, and let's say this object stops here after moving 5 meters. Initial velocity 5 meters per second, and this object stops due to the friction force, of course, when it covers 5 meters. Now question, find coefficient of the friction. Now due to the conservation of energy method, initial energy should be equal to final. Initial, we have kinetic energy, and what happens with this kinetic energy? This kinetic energy will be spent to overcome the friction. Yes, or we can say friction will take this energy, kinetic energy. So we have a work done by friction force. Friction force times distance. And what is the friction force? Friction force equal to coefficient of friction times reaction force, normal force. For this problem, normal force equal to weight. So now let's continue our conservation of energy equation. mv square over 2 equal to friction force mu mg times distance. Mass cancelled. So coefficient of friction equal to v square over 2gx. Velocity 5, to gravity 10, 5. So what will be answer? 5 over 20, 1 over 4. So coefficient of friction, as you see, equal to 0.25. So this is a coefficient of friction. So in this way, you need to keep solving problems. And in next video, we will solve some more a bit difficult problems. See you later.